Thank you all so much for having me, and I hope that you'll allow me to offer some more experiential remarks about the field of exoplanets in the past decade or so as the first speaker of this symposium, to offer a more human perspective a little bit on what it's been like to study exoplanets in the past decade, which basically comprises the entirety of my own career as an astronomer. And it's one that I think is well characterized by a metaphor that I first heard when I was starting as an undergraduate student at UC Berkeley. The metaphor applies for accruing scientific understanding of any concept, but it's a visual one. So the way that this professor described it to me, a very young student and just embarking on the study of physics, was that it often feels, especially when you're beginning to try to understand something, as though there's a wide open ocean of things that you don't understand. When you do take your first few classes, you understand a little bit here and there, some outcroppings of rock, but these concepts seem disparate to you and unconnected. It takes much longer to not only understand more of the surface area of these individual fields, but also to understand something of the complicated, previously underwater landscape that connects concepts which seem to you originally to be disconnected, until ideally you understand all of the field, or you have a more complete understanding, if such a thing ever really exists, as complete an understanding as you can have. And I want to use that analogy to describe exoplanets to just start, although the bulk of my talk will be specific to the outcomes of transit surveys. So in 1995, we had wide swaths of open ocean where we understood very little about the existence of planetary systems other than the single one in which we reside. But we did know, as of 1995, that planets exist outside the solar system. Moreover, because that first planet that we uncovered is unlike any planet that we know in the solar system, we know, therefore, that the solar system blueprint is not universal. By 2005, this is when I was just about beginning my PhD study, we knew that at least 1% of Sun-like stars host planets of some kind. It could even have been tens of percent. This was the understanding at that time. If you were a person who was really interested in exoplanets, it might give you pause for a moment, because it seemed like only 1% of Sun-like stars hosted the types of planets that we by and large were sensitive to, although not all of them, which were these hot Jupiters. So only around about 1 in 100 Sun-like stars, which is more than 0, but still, one might argue, relatively rare. We knew, moreover, that it was possible to detect the molecular content in extrasolar planet atmospheres, although this first detection of sodium was an atomic line. We knew also that stars across spectral type host planets. In fact, only the 9th exoplanet discovered around a main sequence star was discovered around an M-dwarf. So it wasn't long into our discovery of exoplanets generally that we understood that exoplanets do not only occur around sun-like stars. And finally, we were getting some kind of hint tying the conditions of planet formation to planetary outcomes today, that things like the content of metal in the atmosphere of stars seem to be linked to whether or not at least hot Jupiter planets formed around those stars. Here's where we were in 2015. So now we understand more of the occurrence rate across spectral type. Moreover, that occurrence rate varies with period, and it varies with radius. And this is an outcome of both transit surveys, which I've emphasized here, and also radial velocity surveys, which of course Stéphane will talk about next. We had detected particulate sizes of dust particles in exoplanet atmosphere, so in particular with the planet GJ1214, the lack of transmission features perhaps connotes something of the particulate size of dust particles. We had the first images of planets. So in 2009 was the first time you could actually look at an image and conclude that what you were seeing was an exoplanet, a picture of a planet. It's still far from Carl Sagan's pale blue dot, but it was a beginning. And seeing the HL Tau image from ALMA, I think, to not be impressed by an image like that, you would have to check yourself for a heartbeat. And finally, we also know now that stellar metal content affects not only whether planets occur, it affects the dynamic of those planets too. And I'm thinking here about recent work by Becky Dawson, Lars Bucave, and others. So let's say that we wanted to be in this place by 2040. Now I'm going to give some scientific results that would be of my wildest dreams. And they would be the following, for example. So this could be 2040. It could very well be 2100. But what might lie ahead if you were a person who is trying to imagine having spent your entire career seeing our knowledge of exoplanets increase seemingly exponentially? What would be the things you would most want to know? And for me, it's not only the question of whether planets residing in the habitable zones of their stars exist. That question is answered. We would like to know the other conditions of habitability. How often do those occur, including plate tectonics, for example? The occurrence of biomarkers, I think, is one we'll hear about more later today from both Laura and Henriette. I would like to know how stellar activity imprints itself and codes itself upon the atmospheres of planets and maybe even changes whether or not the evolution of life occurs on those planets. And even one might imagine the detection of microbial exolife. I think it's rare to find an exoplaneteer today who would think microbial life is probably not common, although that's a very flat prior, I would say. So let me just highlight a few recent results, kind of contextualizing what we've learned from recent transit surveys and going ahead to one particular transit survey, predicting what we'll find. And I'll highlight a couple results of my own to try to understand that, to play some kind of role in the story that's unfolding. If we want to be at this place where we've detected microbial life by 2040, what are the questions we ought to be asking today? And I contend that there exist links between the ensemble understanding of exoplanets, which now number in the thousands, and the kind of risk assessment calculus, which we'll all be performing in short order to figure out which exoplanets deserve our follow-up resources, including the most precious follow-up resources of all, which are those from space and the largest ground-based platforms. So a couple of those questions, which I think we can answer today, are the fate of planetary systems on evolutionary timescales, and moreover, what's an average type of planetary system in the Milky Way? So my colleague and friend John Johnson likes to say, in the period of time prior to the launch of Kepler in particular, you would often receive in public talks questions like, is the solar system a very typical planetary system? And he would hedge, we all would hedge, because we didn't have the data to be able to answer a question like that. And now we know the answer, and the answer is definitively no. The type of solar system that orbits our own sun is different from the average system by virtue of the fact that we orbit a very different kind of star than the typical planetary system orbits in the Milky Way. And secondly, where will these planets, so you've heard of thousands of them existing, but where will the planets most amenable to follow-up come from? And taking into account what we know about the thousands of exoplanets that have been detected today, what can we predict about the ones that will soon to be found by, in particular, NASA's TESS mission? So I think any talk about exoplanets ought to start at home with our own solar system. This is a movie gathered from NASA's Solar Dynamics Observatory in 2012 during the transit of Venus. And yet you can see that Venus transiting the face of our own sun is not the only dynamic part of this movie. So it's been sped up to just a few seconds for the 13-hour transit of Venus, and yet even in that short amount of time, you can see a hint of our sun's rotation and also something of the beautiful roiling surface of our home star. And yet, if all of this beautiful resolution was collapsed to a single pixel, you still could infer the presence of Venus, because our star would look some fraction dimmer every time Venus transited in front of the star. And this is the single science driver behind NASA's Kepler mission, launched in 2009. It's essentially a single silicon eye, and it affixed its gaze to a part of the sky and almost didn't blink for a period of 5 years. It's about the size of your outstretched hand, held at the end of your arm, and it's overhead in Boston around the middle of July. So this is the sum total of the position of transiting exoplanets that we knew about in this part of the sky prior to the launch of Kepler. This is actually a cluster, too. So TRES-2 was the only known transiting planet in this part of the sky prior to the launch of Kepler. And as of 2013, this was the position of all of the known transiting planets. Of course, keep in mind, these are only planets that reside in the luckiest of all geometries, where you would actually see them transit in front of their host stars. So for every one of these planets, many, many more must exist in order for us to have seen the planets transit that we have. And Dennis Overby of the New York Times referred to this as the Skittles diagram. And the color of these skittles connotes some information that I would like to convey just briefly. We all know that exoplanets are common, how impressive this image is, generally speaking, but what I want to draw your attention to is twofold. So first, the red skittles, things that are approximately the size of Jupiter, 10 times the radius of the Earth, give or take, are relatively rare. So what that meant was that when we were sensitive to exoplanets only from the ground, that were Jovian-sized planets very close in to their host stars, we were sensitive only to the very lowest of the low-hanging fruit. And all of these tasty planets were just outside of our reach from what was detectable from the ground. It took the launch of a space platform to find many small planets, although of course many were detected using other techniques too. And the second thing I want to impart is that the vast majority of these planets, Leslie Rogers, my colleague, likes to say that 80% of the planets detected by Kepler and the planets that must reside in the Milky Way by virtue of the detection yield from Kepler are intermediate in size between the Earth and Neptune. So kind of in between 1 and 4 times the radius of the Earth, between the largest of the terrestrial planets in our solar system and the smallest of the ice gas giants. 80% of the planets in the Milky Way, probably, and yet 0% of the planets in our solar system. It's only one way in which exoplanets comprise a very unique laboratory for us to understand ourselves. So in order to properly talk about Kepler, I'll first talk about a single planet. What's that? Oh, yeah. Pardon me. Thanks.
No problem.
I'll first talk about one of the 4 planets. So I used to kind of be in the business of validating and characterizing individual planets, and no longer. But this is one of the ones that I focused on. It's Kepler 93b. So have a look at this light curve. You can see the decrement of light every time the planet Kepler 93b, which is about 1.5 times the radius of the Earth, passes in front of its host star, which is approximately sun-like. And every time it does that, it blocks 218 photons out of every million from reaching Kepler's silicon eye. But the thing that's so amazing about this, now Kepler 93 is one of the brightest stars in the Kepler field, and it's one of the brightest host stars of the Kepler yield. And this particular planet has a very short orbital period. So we're seeing this transit many, many times around a bright star. But some of the promise of Kepler is borne out in our understanding of this transit depth. We know every time the planet passes in front of this host star, it prevents 218 photons from reaching the detector, plus or minus 1 photon. Is how finely we are able to measure the decrement of light. And yet, the light curve of Kepler 93 doesn't only encode transits. It also encodes the pulsation modes of the host star. This is work that was led by Bill Chaplin as part of the Kepler Astroseismic Consortium to try to understand this planet better. So what you're seeing here is this comb of frequencies corresponding to the resonant frequencies of the star. And what's interesting here is from the 30-odd frequencies that we could detect, you can understand not only something of approximately the sound speed across the star is what's setting the middle of these frequencies here. That tells you something like any sound speed of the bulk density of the object. With the small frequency separation, with the separation between different frequencies, you can also probe the sound speed gradient in the core of the star with astroseismology. That's what tells you how much of that primordial hydrogen has been converted to helium, telling you the age of the star. So with Kepler 93, we were able to measure the size of the star to plus or minus 1%. We know its age to about plus or minus 1 gigayear. And because our understanding of the planet, this is showing to scale the planet and the star, because our understanding of the amount of light that's blocked when the planet passes in front of the star, that error is extremely small. So 2/3 of the error budget is actually set from this 1% error on the solar radius. It essentially means we have a 1% uncertainty on the planet to plus or minus 100 kilometers on a side for something 1.5 times the radius of the Earth. We didn't know the radius of our own planet with that certainty until the Persian scholar al-Biruni measured the radius of the Earth with approximately this precision. It's only one way in which exoplanets now are a field that reflects back on humanity's understanding of our own planet only a few hundred years ago. So you might ask, to what end? That's very impressive to be able to measure something like that, but what is its scientific meaning? And what I'm showing here is a figure from Courtney Dressing. This is showing the mass radius diagram of known exoplanets at that period of time, which transited and for which we had a painstaking mass measurement. So in order to then measure the mass of Kepler 93b, Professor Dressing went out and conducted a very long campaign, painstaking campaign to measure the mass of this planet. There's a lot of planets which are missing from this figure. There exist extremely puffy things, which didn't make this particular figure because she's only including things for which we've measured the mass with greater than 2 sigma certainty. And this entire part of parameter space is unknown composition to us. So like, here's our knowledge of the solar system planets resides down here. This is the only part of this figure which is well understood from planets nearby. So in Neptune, the next thing that we know about nearby is 4 times the radius of the Earth, like about at the ceiling. So these things could theoretically lie anywhere on this diagram, although you could argue different parts of parameter space ought not to allow for planets. But the truth is, our observational constraints were few at that time. And what Courtney concluded from measuring the mass and knowing the size of Kepler 93b so finely in tandem with other planets is that there exists a very well-defined recipe for rocky planets, and it looks not dissimilar to the Earth and Venus. So that's the last time in this talk that I'll refer to an individual planet. And indeed, it often feels like that attending exoplanet conferences now. It's relatively rare to hear talks about individual planets unless those planets are very special indeed. So I mentioned earlier that the average type of planetary system isn't around a sun-like star at all. It was maybe one of the most surprising results from Kepler, at least for me. This is one of my favorite figures from the entire mission. It's dense with information, so I'll walk through it slowly. This is showing results from Andrew Howard from 2012. This corresponds to planet occurrence for planets interior to an orbital period of 50 days or so, but this work was later borne out by Heiss Mulders to be about an AU. So this is showing as a function of stellar effective temperature, what's the approximate number of planets per star. So let me first draw your attention to the numbers along the top here. This is showing the number of stars that went into the calculation in each of these effective temperature bins. And you can see most of them are around sun-like stars. And this is reflecting the science driver of the Kepler mission, which is to establish the frequency of Earth-sized planets orbiting sun-like stars. Yet you can see something very interesting is happening, which is that, especially for the smallest planets, things which are between 2 and 4 times the radius of the Earth, at least on this plot, they seem to increase in occurrence. As stellar effective temperature decreases, of course, stars go off further here. But Kepler looked at hardly any of them. And yet what we see now is that they host small planets in greatest abundance. You can also see here what we were sensitive to from the ground. So for a sun-like star and a Jovian planet about 10 times the radius of the Earth, you can see indeed about 0.01 planets per star, the 1% occurrence rate that we were finding on the ground. So what's so promising here to a person who studies exoplanets is not only are small planets most common around small stars themselves are the most ubiquitous in the Milky Way, and yet you can't see a single one with your naked eye. So if all of a sudden you could see small planets or small stars with the naked eye, and we were sensitive to them, they comprise about 70% of the stars in the Milky Way. This is our galaxy's silent majority. And if you could suddenly see them, you would see 7 or 8 stars appear in the night sky for every 1 star that you can see with the unaided human eye. So what that means is that our galaxy is awash in planets, first of all. And second of all, if you were a young person interested in studying exoplanets, you might pivot to studying planets around small stars. It'll really be the focus of the rest of my talk, even though planets around stars like our home star are sort of uniquely interesting, I think, in some ways to human beings. So to talk about an average type of planetary system, I've argued, is to talk about a planetary system around an M-dwarf. And again, let's go back to home for kind of a model of what we know best. So let's look interior to the orbit of Mars. This is showing a top-down view of the orbits of the terrestrial planets, approximately to scale. And for comparison, this is the number of the multi-transiting systems that Kepler uncovered. So you can imagine you're very lucky in order to see one transiting planet, but your luck can increase yet more. You could see 2 transiting planets. You could see as many as 6 transiting planets, in the case of TRAPPIST, 7, I think it is now, orbiting the same star. And so let's compare in sort of broad swaths our sun with a typical, seemingly typical planetary system orbiting an M dwarf. And you can see in comparison, they're not so dissimilar. Our sun hosts 8 planets, depending on how you count a planet. Roughly, approximately 2 reside in our star's habitable zone, depending on how you define the habitable zone. And we're very close to being coplanar. So if you were to fit a Rayleigh distribution to the mutual inclinations of the orbits in the solar system, it would peak around 2 degrees. The biggest degree of misinclination is about 7 degrees. And in the case of Kepler 186, it has 5 transiting planets, so it has to have at least 5 planets. At least one of them resides in the star's habitable zone, and those planets all must be aligned to within 8 degrees in order for them to all transit. This is showing a top-down view. So Kepler 186, in order for a planet to reside in the habitable zone, that habitable zone is much closer in because the star is so much less luminous. So this is showing a typical 6-planet system from Kepler 11, and I had the idea with a colleague, John Johnson, to undertake the following experiment. So let's say now that you are looking at this planetary system edge-on. Depending on the degree of coplanarity and the number of planets in the system, that'll dictate the number of planets, the number of transits that Kepler's eye will see. If the mutual inclinations are higher on average, you ought to see less planets transit. And this is the sum total of the data that we use to conduct this study to try to extract what is a typical planetary system from the Kepler transiting data set. This is particular to M dwarfs, again, so I've focused just upon M dwarfs for this study. This is all of the data that we used for this study. It's a vector of 5 numbers. It's the number of transiting planets per star for the 100-odd M dwarfs around which Kepler found a planet. So for the vast majority of the M dwarfs around which Kepler found a planet, it found only 1. And that makes sense geometrically, but sometimes it found more, including up to 5 for Kepler 186, for example. And so we decided to draw toy planet models according to a 2 axial parameter space. One of those things is the number of planets per star, and the other is the average scatter in their mutual inclination. So we wanted to know, is there a stamp that you could carve with a particular kind of planetary system, stamp it isotropically all over the Kepler field, and basically reverse engineer what Kepler's yield was for planets orbiting small stars. And there's no necessarily reason a priori to believe that different parts of this parameter space won't be populated. So this would be, for example, a 6-planet system perfectly coplanar. The solar system, in contrast, resides right around here. Although for hot Jupiter systems, we know that there are systems where there seem to be less planets with very high mutual inclinations. Hot Jupiters only extremely rarely host an additional transiting planet. And so this is what we get. This is the marginalized posterior distribution in this part of parameter space if you try to fit all of this data with a single type of planetary system. So what we found, first of all, is that this type of planetary system, it doesn't do a particularly good job of replicating what Kepler saw. I would also argue this is a little bit disfavorable from a dynamical point of view, in the sense that these are very high mutual inclinations, but we know independently from radial velocity work by Marianne Limbach and others that the really multiplistic systems from radial velocity have very low eccentricities. So to have really high mutual inclinations and low eccentricities doesn't make sense kind of from an equipartition point of view, but more than that, this isn't a good fit to the data. And so what John and I did was the next simplest thing, which is to adopt a mixture model. So now there's 5 free parameters: the number of planets in the first type of system and their mutual inclination, average mutual inclination, the number of planets in the second type of system and their mutual inclination, and the fraction by which nature makes them in one type of system versus the other. So you can see now, first of all, this furnishes a much better fit to the actual observable of number of transiting planets per star. These are 2 very well-separated parts of parameter space where you have 2 very different-looking planet systems around M dwarfs. TRAPPIST, for example, the next year resides right around here, was discovered to reside right around here, extremely coplanar. And So now this is showing the marginalized posteriors just for this first population up here that look very, I'll call it TRAPPIST-like, very flat, manifold planetary systems, probably extremely low eccentricities too, from what we know from radial velocity. So on average, a mutual inclination of 2 degrees, you need at least 5 planets. And more than that, half of the time, known transiting systems are occurring in this type of configuration, this like TRAPPIST-like configuration. This is just for transiting planets, by the way. So there's a bit of an important point to make here, which is that this isn't the underlying number of planetary systems, because these types of systems which have more planets and are flatter are likelier to show a transit of some kind. So they're overrepresented, I would say, among planetary systems. So I wasn't the first to argue that there exists evidence for 2 types of planetary systems, and in fact, it's still really an open question in the community whether 2 types of planetary systems are really necessary to recover what Kepler saw. But there's many ideas, one of them being that self-excitation is possible. And what a bummer I think that would be if indeed that's what was happening. If all planetary systems, give or take, in the Milky Way, are approximately around M dwarfs, start in this type of flat architecture, and then over time, planet-planet interactions cause them to self-excite out of the transit geometry, maybe in a catastrophic way. And that over a metastability timescale of a gigayear or so, approximately an evolutionary timescale. That would really be a shame if the typical laboratory for forming life in the Milky Way disrupts as soon, arguably, as life gets a chance to form. Or perhaps this dichotomy originates with formation conditions. And so this is showing now like a comparison eyeball between the breakdown of the types of planetary systems that Kepler saw orbiting M dwarfs. So 50% of the time, this type of 5-planet system, at least 5 planets. The other 50% of the time, something else happening altogether. I'm showing here a hint of another piece of information, which is that stellar obliquity seems to change. This is work from Morton and Wynne. So with a multi-transit system, it seems like the planets are better aligned with the spin axis of the host star. Another kind of piece of evidence that we wonder, is it tied to formation or subsequent planet evolution? And so with a Yale graduate student, Jack Moriarty, a few years ago, we undertook a study which was asking if we model late-stage planet formation with N-body simulations, where we take hunks of rock intermediate in size between the moon and asteroids, and we distribute them according to 2 different parameters: the total amount of mass available in this disk and the surface density power law that defines how that mass is distributed, and we evolve it forward in time, then what are the types of planetary systems that result, first of all? Second of all, how stable are they? So running them for very long periods of time, up to a gigayear, for some of them 10 gigayears, although rarely because they're costly simulations. Can we replicate what Kepler saw? And so that's an argument that I would make is twofold. First of all, we can explain these 2 types of planetary systems that we need to recover Kepler's yield around the small stars with 2 types of disks, but we also favor this frozen-in hypothesis, which is that once the type of planetary system forms, by and large, it doesn't change. Again, though, this is an open topic in the community. And yet it's not only the number of transiting planets per star, it's incumbent upon any model to explain the Kepler yield to replicate all of the observables. Not only the number of transiting planets per star, but things like the period ratio of adjacent transiting planets and the transit duration ratio. This is probing something of the chords across which different planets are sweeping. So this is showing not fitting to these distributions. This is the observed population from Kepler in blue. This is taking what we would assume for the mixture of these 2 types of planetary systems and taking a guess for what then we would predict for these other observables. If you have these 2 types of disks furnishing these different populations in the same measure, it produces a self-consistent it has a self-consistent ability to replicate what Kepler saw, not only in the number of transiting planets, not only in these other observables, but also in the period distribution. So it's a phenomenological result. If you were to ask me, well, doesn't nature much more often make things according to some gradient rather than in 2 different toy models? I would argue that that's true. That seems to be true to me. But phenomenologically, this does a very good job of replicating what Kepler sees right now. And there's other reasons to be very interested in this, which is that very similar work from Dawson, Lee, and Chang argued that these two types of planetary systems should have very different eccentricities. This matters the most for M dwarfs. So in order to be in the habitable zone orbiting an M dwarf, you have to be huddling very close to that campfire in order to be warm enough to be comfortable. But what that means is that even a very modest eccentricity can induce a sterilizing tidal greenhouse effect. That's work from Rory Barnes that I'm thinking of. So depending on exactly how what the planets are made of, so how they dissipate energy tidally, and exactly what mechanism you're talking about for dissipating tidal energy, the cutoff for when things get dangerous and eccentricity is sort of blurry. But I've placed it kind of here, it's sort of in the middle. And what that means is that planets in this type of TRAPPIST-like system are sort of uniquely inoculated against this effect. One might argue then, and Becky found the same thing using her simulations, Professor Dawson, I should say. And so what that argues is that, well, if your follow-up targets are going to be M dwarfs, well, then you ought to be drawing them from this particular type of simulation if what you're interested in is perhaps a more habitable system. There's also maybe even some evidence that the bulk density of planets is different between these two types of systems, and maybe that makes sense given the fact that if you believe that their formation conditions are different, resulting in these different outcomes in their hill spacing, then similar work by Becky argued that the planet bulk density ought to be tied to this. So she did very similar simulations to Jack and myself, but unlike our work, she painted on gas onto the simulations to see how it would accrete onto planets and the types of planets it would form. So this is showing, I'll go back for a moment, the distribution in hill spacing between adjacent planets. So how closely are the planets spaced? In these two types of populations, the cooler one looking like TRAPPIST, the hotter one where there's either less planets or they're very mutually inclined. And what Becky is showing here is that as a function of hill spacing between planets, it ought to be a probe of the bulk density of planets. So rock is about here, 5. So what she is arguing is that planets which are closer in, like tightly packed, ought to be fluffier. It's an attempt to explain why planets whose masses have been detected with transit timing variations are on average lower density than radial velocity planets, although there's an argument there that that's just due to bias. What I'm arguing here is that there's a real confluence between observational and theoretical work using ensembles of planetary systems to make arguments in advance, maybe even about the composition of planets, let alone like where they're spaced relative to one another and their orbital dynamics. So in the final 15 minutes of my talk, I'll talk about where the planets amenable to follow-up will come from, and using all of the information that I've just argued is extractable from Kepler to make predictions for what the next major NASA mission, with the TESS mission being run out of MIT, will find. So again, here's sort of a breakdown of the Kepler host systems. So it stands to reason that one single type of planetary system, you'll often hear for M dwarfs, 2 or 3 planets per star, on average 2 or 3 planets per star. And yet, if you produce a model with 2 or 3 planets per star, you can't replicate any of the Kepler observables. And so it stands to reason that one ought to use a type of mixture model that reproduces the Kepler results for any other future mission too, if one wants to obtain a very realistic yield. And so it's very timely to do this for NASA's TESS mission. This was a mission which was launched just a couple of weeks ago, actually, if anyone saw the video of the launch at Cape Canaveral, and maybe some people in this room were even present for the launch. So unlike Kepler, which affixed its gaze to a part of the sky and didn't blink for 4 years, TESS has 4 different eyes. And every single one of the focal planes for a single camera is about 4 times the size of one individual Kepler field of view. So every about month or so, TESS will pivot so that it covers with its 4 cameras a different sort of half-orange slice of the sky, with the goal ultimately of paving almost the entire sky, looking for transiting planets, which we now know must be there from the Kepler mission. So Kepler only looking at stars in this part of the sky on average hundreds of light years away. TESS is then the next stepping stone. Knowing that those planets are there, they must be nearby. Well, around which stars are they nearby? So this is showing the TESS footprint. Unlike Kepler, it's extremely complicated. There's parts of the sky that receive almost a year of coverage, and they're designed to coincide with parts of the sky that the James Webb Space Telescope can look at as much as it likes. But most of the sky gets only 27 days of coverage. So a study led by Peter Sullivan in 2015 made a prediction for the number of planets that TESS ought to find. And TESS is looking at all 50 to 80,000 of the nearest M dwarfs. So all of them are receiving basically a 2-minute cadence from TESS to try to uncover planets around them. But what recent work I've undertaken is to not use a model that assumes like 1 or 2 planets per star, which has been done in the past, but rather to apply this mixture model. So what I decided to do was take this sample of known underlying population of M-dwarf planets. So this is showing as a function of radius and as a function of period how we think M-dwarf planets appear in nature. They tend to peak around 2 times the radius of the Earth. That's where nature is producing most of them. And then in Peter's paper, we have this yield for what was actually detected by TESS. So what Peter did painstakingly is to take into account exactly how TESS is sensitive to photons as a function of different parts of the sky, how much contamination you're getting from eclipsing binaries, the different noise budgets for all of these different stars, and he did a star-by-star injection and retrieval analysis. One piece of data which is not contained in that paper, but I contend is extractable from it, is the TESS completeness. Now, so it's hard to talk about completeness of emission to different planets when it's looking at different parts of the sky for different amounts of time. But there does exist some ensemble completeness, which is a weighted average of all of the individual stars. And I think if you know what was injected and you know what was recovered, one can extract that completeness and then use that completeness with a much more realistic population of planets to make different conclusions about what TESS will find, not only about the number of planets, but their orbital dynamics and other things too. So this completeness function. So that was the first thing I did, was to extract it. Then you can take this much more realistic model for planet occurrence that recovers what Kepler saw, filter it through this completeness, and make conclusions about what TESS ought to find. What I conclude is that you'll find at least 50% more planets. So by virtue of the fact that TESS is looking at an average star only 27 days, there's an extremely strong preference for that type of planetary system with many planets very close in. So there's something like 20% of the planetary systems in nature look like TRAPPIST. They're already overrepresented in Kepler. They're 50% of the types of planetary systems Kepler detected. For TESS, by virtue of the fact that it looks at the average star for only a month, these are going to be 75% of the types of planetary systems that TESS sees. And there are 0 multi-transiting systems predicted for TESS from that original work, where at least 20% of them are going to be multi-transiting systems that TESS itself will find. And you can make dynamical predictions too, and even using work from Professor Dawson, bulk density predictions. And so that's what I'm showing here. So this is the real Kepler data in red. The gray is the mixture model that I derived as part of Ballard and Johnson. This is showing the contribution of the original dynamically cold and dynamically hot populations. And this is the period distribution too. You can see here that you also need a contribution of both models in the same measure to reproduce the periods of what Kepler saw. In contrast now, taking that and filtering it through the TESS completeness, this is what I think TESS will find. There will be some fraction of TESS stars where you're seeing 2 and even 3 transiting planets around the same TESS star, and of course peaking toward much shorter periods. So these are now going to be 70, 80% of the types of stars that TESS will see. But moreover, because TESS is not as sensitive a photometer as Kepler, there's going to be an enormous number of transiting planets in known TESS systems. So where you've discovered at least 1 transiting planet with TESS, which will elude detection by TESS proper. That's because TESS photometry isn't sensitive enough to detect things on an M dwarf on average between 1 and 1.5 times the radius of the Earth. So I'm showing here kind of a bouquet of systems around which I predict TESS will find a single planet with kind of an average period distribution. And on average, TESS will miss some number. So I quantified it in the paper I wrote recently, but let's say take an average 200 TESS stars around which a planet was detected. So around an average 200 stars from TESS with a detected planet, there'll be 250 planets. So some stars host more than one. Among those, there'll be about 130 planets which transit those 200 stars, which are undetected by TESS proper. What that means is there's going to be an incredible synergy with both ground and space-based follow-up to discover additional planets. So this is showing the number of additional transiting planets in an average 200 TESS light curves in which one planet was detected, which elude detection from TESS proper. They're transiting, but they reside below the TESS noise. So let's say that you have a ground-based survey with even modest sensitivity out to 2 days, and you're looking at M dwarfs, planets around this size, one Earth and a half or so, they're producing like a percent dip. So if you have a ground-based survey, modest completeness out to 2 days with sensitivity to something an Earth and a half, you're detecting 11 planets. That's discovering an additional 11 planets using TESS itself. So there's an argument here that follow-up is going to be uniquely important for TESS in order to understand completeness. And so I think I think I have enough time to talk more about the dynamics that can be inferred for the TESS population. So now this is showing predictions for the eccentricity of these planets. So I've made an argument that if there exist these two types of planetary systems that are necessary to explain what Kepler saw, they also have very different dynamical conditions. If TESS is extremely strongly preferring this type of very flat planetary system, what that means is that the eccentricities of TESS planets will be drawn from a totally different pool than the eccentricities of Kepler planets. We'll be looking at two very different populations of planets, and that's what's shown here in this cumulative distribution. So for Kepler planets that host a single transiting planet, you can see, or for Kepler stars that host a single transiting planet, you can see that something like half the time these eccentricities are higher than 0.1. Now I've indicated here where this tidal Venus effect occurs. So these planets are in some danger. You wouldn't want to just look at, point your precious follow-up resources at just any random Kepler single transiting planet, because there's a relatively high likelihood that it has the type of eccentricity that would render it extremely difficult for life to survive on that planet, because oceans would probably evaporate. But you're safer with multis, because that means you're much likelier to be drawn from this more circular and dynamically cool set of planetary systems. With TESS, you're safer still. And with systems for which TESS detects at least 2 transiting planets, it's extremely unlikely, to the effect of 1 in 20 or 1 in 10, that if you're looking at a planetary system where TESS sees at least 2 transiting planets, that those are going to be eccentric enough to render you any danger for life evolving there. So again, these are sort of inoculated against this dangerous effect when we're thinking about which precious planets to pick for follow-up resources in the future. And I'll conclude with this transition to more radial velocities, which is that these radial velocity curves are always full of hidden planets. Surely, with TESS, that's going to be unusually strongly true, because so many of even transiting planets will be missed by TESS proper. So I'm showing here now a average TESS planets. If it's offset a little bit, that means the planet isn't transiting. So in this particular system, and this is a prediction for the radial velocity curve up here, where the sum of them is shown with the dotted line, you can see that this one doesn't produce that much of a difference. But many TESS systems are going to be looking like this, where there's at least 5 planets, many of which don't transit. It'll produce changes to the ultimate radial velocity that I'm very curious to see what will happen. It's a study that I'm undertaking now with Jen Burt, another Torres fellow at MIT, to see what will result if you do a follow-up observation of TESS transiting systems, assuming that the transiting planet is the only planet in the system. How off would that get you? On average. And of course, there'll be some for which it'll be very difficult to extract only the transiting planet. And so I offered at the beginning of this talk an observation that I think there's questions we can be answering today to put us in a very good position for the next era, which is this sort of risk assessment calculus of deciding which of these thousands of planets ought to receive follow-up resources, including the most precious follow-up resources. And I'll just answer the questions that I posed. So first of all, in order to understand transit yields, particularly from Kepler, you need a mixture model. I would argue one needs a mixture model, particularly around the most common type of planetary system in the Milky Way, which is a small star. And I would argue it's formation conditions that are shaping those planetary outcomes rather than subsequent evolution. That's a conclusion which I think is favorable also to the long-term evolution of life. Although I've heard it said by other exoplaneteers that there's a list of reasons as long as your arm why life would have trouble evolving on an M dwarf. Moreover, I make new predictions for what TESS will find. I predict it'll find 50% more planets, and also with some dynamical predictions for those types of planets around the M dwarfs alone. The 50 to 80,000 M dwarfs that TESS is going to be looking at will find 1,000 M dwarf planetary systems. 20% of those from TESS alone will have more than one transiting planet. And even short baseline follow-up, for example, with the Spitzer Space Telescope, which was extended, even with CHEOPS, which I could argue there's some set of stars where you can look for a few days. If you look at a multi-transiting system with TESS, for there's at least one transiting planet and if there's two transiting planets, and you look for a long enough time, there's a 50% chance there's an additional transiting planet. This is the type of thing where additional planets will be just like falling out of the tree if you look with the right follow-up resources. And I would argue to this audience that it's both possible and timely to be leveraging our understanding from these thousands of planets that exist now to prepare for the next era when we hopefully might be detecting some more of other atmospheres. Thank you for your attention.
Thank you, Sarah. Now we have around 15 minutes for questions, and we will send a mic around. So, any questions for Sarah? We had one with Mimi. And again, notice that you can't hear the mic, but it is on. Yeah.
Yes. Do we understand how the obliquity of the star and the structure of the planetary system are connected?
One answer is no. There was a paper out really recently led by Diego Munoz, which is making an argument about the stellar planet obliquity. So I would argue that the story of planet and stellar obliquity is one that is shaped by psychology too. So looking like around 2009, there was a lot of results coming out where all of a sudden there were arguments that hot Jupiters in particular were often extremely misaligned with the axes of their host star, even going around like the opposite direction. That the star was evolving, and then there was a particular plot in 2009 which showed that this was a function of stellar effective temperature. So the argument there was that, let's say that you have a hot Jupiter planet, it probably got there, I mean, people argue now that perhaps hot Jupiters form in situ, but at that time the argument was, well, it must have gotten there because of some catastrophic scattering event, and only once the star is like no longer convectively dominated can it like bring the planet, wrench the planet like back into being like a low obliquity. And those results have kind of come and gone. So the truth is I'm not exactly sure like what physical mechanism is causing it. Of course, you're probably thinking the same thing as I'm thinking, which is that in this understanding we have of planet formation with the NEAS model, if it all collapses from the same disk, well then on average they should have very low spin-orbit alignment. So any misalignment might be due to subsequent planet-planet scattering. I think that's generally the argument.
Right, we take the next question from Sophia here, and from now on I will encourage you to say your name before you ask the question, starting with Sophia.
Yes, so my name is Sophia Felsing. Very interesting about the need of further photometric, if I understood correctly, ground-based follow-up. So I guess now is the time to actually start preparing that, because when the test data will come, it's not that many years to go, right?
Yeah.
So what is happening? Are you aware of efforts on that?
Yeah. So usually giving this this talk, I argue, if you have a ground-based survey that has moderate completeness out to 2 days, what I'm really saying is, what if you're Mirth, or if you're Trappist, for example. If you choose to conduct a survey like this is the number of planets you'll find. But it's also an argument for building very cheap transit follow-up surveys now. And that's an argument I've made for faculty at different universities who have access to even like $50,000 I know that sounds like a lot of money to an average human being, but to purchase off-the-shelf components and have a survey like that, you're guaranteed to discover planets, and that's a very rare guarantee to be able to make.
Right, we have a comment from
I
Stéphane.
just want to comment on the question because we have in parallel there is a set of 12 robotic telescopes called NGTS that are exactly doing that. So on the small stars from the ground you can reach a depth that correspond to super Earth in good condition. So, but that will work fine for the M dwarfs actually, and they are faint. So NGTS will be the perfect follow-up machine for TESS. And of course for brighter star, then we can go to CHEOPS from space.
To use CHEOPS to just stare at a single star, I sense, I don't know, that would be
Yeah, but
like
if you do follow-up, you
Yeah,
will just target one main star.
We have a question from Georgie.
Georgie Coquin here. I have a question about one of your dream observations, so to speak. So, how would you go about detecting tectonic plates on exoplanets?
Yeah, or like signatures of them.
Exactly.
I've been thinking about this. Okay, so one possibility is to be able to measure the eccentricity at all. So there's some arguments about like having plate tectonics not necessarily from the mechanism that we have them here on Earth, which is radiogenic heating. So let's say that you didn't have radiogenic heating on a type of planet orbiting an M-dwarf. You could still induce plate tectonics necessarily. You would induce plate tectonics with like a particular amount of tidal excitation. Well, that's technically happening on Io, for example, although no one would call Io habitable, like constantly being repaved by volcanic activity. So take that on one end. On the other end is Mars, which is tectonically dead. So surely in the middle, there exists some place where necessarily the planet is probably, knowing what we know about what rocky planets are made of, necessarily it must have some like molten content in the center is one argument. Although I think there would be atmospheric signatures too of volcanic activity or a carbon cycle or something like that. But again, these are like of my wildest dreams also. So I can cross my fingers, but what I actually suspect will happen is that someone will think of a signature to find something like that and that we would go looking for it.
We do have a geologist in the room who might be able to help us with that.
We can take that
Oh
over
no,
lunch.
Vigor's not here. Okay, I'm sorry.
We can
Whoever this
solve that
geologist
question
is.
over lunch, I would say.
Yeah, I would love to hear that.
Okay, maybe I can break in with a question here. So you had this kind of two populations. You had the ones that are low multiplicity and stirred up, the ones that are high multiplicity and very low mutual inclination.
Yeah.
And you say you do not like the idea that they evolve with time. And I understand your point. If
Yeah.
everything starts with high multiplicity, low inclination, then
Yeah.
kind of goes self-unstable. It's not so nice for life. And so
Yeah.
on. But I wonder, I think a key to testing this idea would be to understand the ages of the
I know,
planetary system.
yes,
So can I ask you about that?
Yeah.
What are your thoughts about determining ages of M dwarfs and correlating that with the planetary systems?
That's one thing where I would be happy to be wrong, because then if I knew I were wrong, I would know the answer. You know, I would be happy to be wrong. So it's something I've been thinking about with TESS recently, and I thought, my first thought was, well, with TESS, because it's a full sky survey, you're going to be probing systems which have higher and lower galactic height. So immediately I was thinking, oh, could we use galactic height as a proxy or something? But it's all thin disk is the thing. So in talking with Elizabeth Newton, who's a Hubble Fellow at MIT right now and an M-dwarf expert, she argued you should use activity. So let's say that the time scale for instability, I don't know, in like Poo and Woo or something, they would argue like 500 million years, like maybe a giga-year, it takes to disrupt the primordial configuration to one that's dynamically hotter. Well, there are M-dwarfs which are active on about that time scale. So like an M0 and M1, these are stellar types where they're active for about a giga-year or 2 giga-years. So that's something where if you had enough types of planetary systems, you could compare to see, is there a difference between the types of planetary systems around active stars and inactive stars? And that's something I'm seeing now. If it's possible, then it would be like quite noisy to do it that way. I mean, because I was working on it now to see if it's possible. But there's another technique altogether, which has been proposed by Phil Muirhead, who's an M-dwarf expert at Boston University, who argues that extremely high resolution spectra of M-dwarfs extracting information about alpha enhancement should make it feasible to know the ages of M dwarfs. Now that's a theoretical argument, but it could well pan out. Yeah, of course, rotation too, and other proxies for age.
Sophia has a comment on that.
So Sophia Felsing, I am not sure about your alpha enhancement. What would be your foundation for that?
For which part?
For the alpha enhancement to be a proxy, I mean, the proxy for age there is potentially there, but it's very low. What about rotation?
I saw him say this in a colloquium.
What about rotation? Can you measure that in M dwarfs?
Yes, you can, and much more easily, I would say, because they remain active for longer. So there's no difference between the multis and the singles within Kepler for there being like a quicker rotation around the multis. So, or like galactic height, or something like that. So arguably one could use gyrochronology to make an argument about relative age. And that's feasible. I think, well, so I wouldn't call myself an M dwarf expert, although I'm very interested in their exoplanets, but M dwarfs themselves, I think, are mysterious enough that I only propose to understand them kind of. It seems like there's some combination of things, including like their like galactic velocity, their like rotation rate, their activity, whether they show H alpha in emission, like all of these things kind of speak to like age in some way, but to be able to pinpoint an age to plus or minus 1 gigayear is another question altogether. So what Phil proposed is that there's a way to do it with alpha enhancement. He has a paper out about it, and I ought to understand it better before I argue that it's possible. But I found it convincing at the time. Muirhead is his last name. M-U... Oh, yeah.
Okay, we have time for 1 or 2 more questions. We have Ross here.
Ross Church. So if you have an RV curve where you're seeing the effects from lots of planets superposed, and you have the orbital period of one of the planets from the transits, can you do some sort of spectral filtering and still be able to recover the mass of the planet?
That's probably a question more for Stéphane than myself. So the study that I'm undertaking now is basically asking, if you went into it assuming ahead of time that there's probably 3 or 4 other planets there, would you make a different conclusion? Like, so if you change basically your prior on the amount that other planets are impacting the radial velocity curve altogether, will that change the mass that you infer? So that's testable, and that's the question I'm asking. The wizardry of extracting a mass from radial velocity is something I would defer to another person to ask. I know that spectral filtering is relevant.
Right. Any final question? We have one from Paul, so you can send the mic back.
Another question from the same place in the audience, yeah. Paul McMillan. So my understanding of the TESS survey is that there's an input catalogue of about 200,000 high cadence. Do your results presumably depend in, very, very critically on how that is chosen? So does this give you an opinion on how it should be chosen, and have you had any influence?
Yeah, so that same Phil Muirhead at Boston University had a paper recently about the TESS input catalog for M dwarfs. I'm kind of in no danger here of the catalog changing in any way, producing a change to these results, because essentially every M dwarf is already on the short cadence list. So, and also like the only habitable zone planets, arguably speaking, that TESS is going to find are going to be M dwarfs or maybe light K, which is why if TESS is kind of like a finder camera for JWST, which I've argued like, okay, if you're trying to find targets for James Webb, all of the habitable zone planets, and especially the Earth-size ones, are going to be around M dwarfs, which is why the mission rightfully is just chucking every M dwarf within 50 parsecs onto the short cadence list already. There's no more to add or take away.
I think with that answer, let us thank Sarah again.
Thank you.
Very much.